Good morning. My name is Dimitrios Papavassiliou, and I will present the paper on hydrodynamic induced stress distribution experienced by VWF protein models. This is work that has been done by my undergraduate student, Sam Fair, who is currently in medical school, and by Wok Nguyen, who was a postdoc at the time and now is back in his native country of Vietnam. The motivation for this work is our interest in looking at mitigating heart disease effects and cardiovascular disease. According to the World Health Organization, heart failure, heart disease is the leading cause of death in the world, even now with COVID-19. In 2014, over 5 million people in the US were affected by heart failure, and we had hundreds of thousands of deaths every year due to cardiovascular disease. So it is quite common to use implants, from the simpler ones like heart valves to more complicated ones like ventricular assist devices or VADs for patients who suffer from heart failure, especially when transplantation is not important. But when such type of intervention is done, many patients may suffer from hemolysis, or they might suffer from blood clotting abnormalities. And these abnormalities are often related to the VWF, the von Willebrand factor, which is a protein that flows with blood. So when the VWF flows inside the blood in physiological conditions, there are no problems. That's what this is what happens in everybody's heart. However, when you have a medical device like this VAD here, shown here, you might have the case of non-physiological flows. You might have turbulent flows, you might have extensional and shear stresses that are being applied on the blood and on the VWF that are not physiological. So the function of this protein might be affected by its configuration. And if it is either stretched or squeezed or any changes in its molecular structure due to the flow field, it will lead, a patient might suffer from what is called the von Willebrand syndrome, which is connected to difficulty in clotting of blood and anemia. Also, when people might have internal bleeding, the bleeding might not stop, stomach ulcers and things of that nature. So the motivation for our work is to answer a question: what is the shear stress and how does the shear stress can affect the VWF? And if you can calculate the average stress inside the medical device using CFD or theoretical calculations, is that enough, or will you have a problem when you design such device? And if you can calculate the distribution of stresses and the history of the VWF molecules as they travel in the flow field, what would these effects be? So we go about this by doing computations. We compute using direct numerical simulations the details of a flow field in turbulent and transitional flows that are commonly found in medical devices. And we calculate the trajectories of models of the VWF molecules. And this is a Lagrangian approach. And then we use the information of the flow field to calculate the shear stresses and get the stresses along the trajectories of the VWF molecules, models of VWF molecules that move into the flow field. And one way to do this is through an Eulerian framework. So you have a window of observation and you have the models of the VWF molecule to go by, or you can do it with the Lagrangian framework where you follow the trajectories of models of this molecule and you calculate the stresses along the trajectories. And this is the approach that we follow. We have a Lagrangian approach, so we follow the trajectories of these molecules in the Lagrangian framework and we calculate the shear stress along the trajectories of VWF molecules. So we tried a couple of different cases. One is typical flows that you find in something like a blood pump. So the blood comes outside of the body and follows through a blood pump. Actually, the one here in the figure is a blood pump that was proposed by the US Food and Drug Administration, a centrifugal pump that they proposed to people who do CFD for biological flows to simulate. So we picked the Reynolds number in this part here, what's called a sampling port here. The Reynolds number for that case was 3600 roughly, and we created a direct numerical simulation for this Reynolds number and blood flow. Another example, another case we looked is the Poiseuille flow that you have when you have a ventricular assist device. So this is a typical ventricular assist device. So here in this space between the casing of the pump and the moving part, you have quet flow because this is a moving part that rotates on the order of thousands of RPMs. And you have also a pressure drop, so you have a combination of Poiseuille and quet flow. And so we tried to simulate that case as well with canonical typical flows. So the numerical simulation that our direct numerical simulation is a typical spectral simulation for turbulent flows. It's written in dimensionless quantities. So the simulation is all the quantities in the simulation in viscous wall units. So the velocity, the length scales, and the time scales are made dimensionless with the viscosity of the fluid and the friction velocity, which is the square root of the shear stress at the wall and the density of the fluid. In our case, we assume the fluid is blood. And for the Poiseuille flow, fully developed turbulent flow, these are the dimensions of our model channel, and half channel height is 300. And for the quet flow, Poiseuille quet flow, these are the dimensions, and this is the half channel height. Here you see the resolutions for both the Poiseuille flow and the Poiseuille quet flow. And what we do is we follow the trajectories of models of VWF molecules that are released at different distances from the bottom wall of the channel. So Y0, Y is the dimension that is vertical, perpendicular to the wall of the flow of the channel. And when we say Y0, the VWFs are released here at the bottom of the wall. When we say 300, they would be in the center of the box, and so on, at different distances from the wall. And we pick these so that we're within the viscous turbulent sublayer, in this case, or we're in the logarithmic layer that have different structure for the flow field, especially when it is turbulent. So the Lagrangian approach means that we release the VWF models, the models of the molecules in different lines that span the domain at different distances from the wall, and we release 100,000 particles at each location away from the wall, and we make the assumption that the velocity, the Lagrangian velocity of the models of the VWF, they follow the Eulerian velocity, and in addition to the movement because of the velocity field, we have a movement because these are molecular models of a molecule, and we have Brownian motion. And in order to get this Brownian motion, we apply a random walk model. So at the end of every time step, the fluid velocity, the velocity of a particle and the position is updated based on the addition of a Brownian step or the movement of the molecule. And this Brownian step is found by assuming that there is a random walk that follows a normal distribution with a mean of 0 and a standard deviation that depends on the time step, delta t, and on the Schmidt number of the VWF. And assuming that we have about 20, let's say 18 nanometer VWF molecules, the Einstein-Stokes equation can yield a Schmidt number that is on the order of 900,000. So this is what we use here to update the particle position after every time step. So when we do that, we can actually follow the trajectories of 100,000 particles for each one of these distances of release from the wall. These VWF molecules, we release them instantaneously. So it's an instantaneous source of molecules. It is as if we put in the blood at one particular location the VWF molecules, and then we follow the trajectories in space. And here are the average X and Y positions. X is the direction of the flow for the Poiseuille flow, and we have the average X position and the average Y position for particles released in the middle of the channel. So you see they're released in the middle of the channel and they have no special reason to go above or below it. So you see that the Y is pretty much stays at 300, and they move in the streamwise direction, in the X direction. Now, we have followed these particles for 300 T plus units, 300 time units in viscous wall units. So that's why the ones that are released from the wall at Y0 equals 1.5, they don't travel very fast. because, and very far in the x direction because the mean velocity for the flow field is very low. So that's the physical explanation of why this looks the way it does here. For this case, when we have the Poiseuille flow, when you release at y03, the top, there is a pressure drop that moves the flow field, but also the wall of the channel is moving in the negative direction in the bottom wall. So initially, when the particles are released very close to the wall, they start moving, they have a little bit of a negative direction, on average, negative position, but then the Poiseuille flow part of the flow field picks up and then they eventually end up being in the positive x space. If you release in the middle of the channel, you remember this is 80, y080 is the middle of that, of the Poiseuille flow channel, they stay pretty much in this location, like this did. So keep this in mind. So when we release particles in the center, they stay in the center. If we release particles closer to the wall, they are initially in that location and then slowly they go away from the wall region. Now, this is the average stress. So we calculate the stress on each particle position, the shear stress, and then we calculate the average of that stress. And you see here, this is in this plot, we have the average stress in plus units, as we do here, but we also have the stress in pascals. And the red line is the critical shear stress that is accepted for damaging the VWF. And you see that when you look at the average stress, a set of particles can start in the bad area above here, they're damaged, and then they might end up on average being below the critical stress, or they might be below the critical stress initially and stay in this area. For Poiseuille flow, they are always in the danger area. Always we are above 5 pascals. Now, if we look at the distributions, look at this case, for example. We have Poiseuille flow. They start at, they're released at 15 or at 1.5 away from the wall. But then as time goes by, these lines are the distributions, the probability density functions of the Poiseuille flow and the Poiseuille flow for the stresses. And as time goes by, these distributions are being shifted to the right. The same here, the same here, the same here. However, you can see that if we have the critical stress, this red line is the critical stress. Let's say, look, we're looking at this case. We have some of the VWF molecules that sometimes are at high stress regions that they can be damaged. As time goes up and up, as you go to 300, remember the average location of the particle is to go towards the center of the channel where the stresses are smaller because the mean velocity profile has a flatter velocity profile. So du dy is more flat, closer to zero, and they don't see lots of stresses. But when they are in the wall region or closer to the wall, part of them, they see high stresses. Now, if we look at the history, that means that we look at the stress along the trajectories of the particles and then we add it up. So we integrate in time. And this is what we do here for the Poiseuille flow. Here is for the Poiseuille flow for different locations, different release from the wall. So you see here that the form of the stress, so at lower times, there is a totally different PDF than it is at higher times. Of course, as time goes by, the integrated stress becomes larger and larger. But there are different forms of it, different profiles. In conclusion, the average shear stress does not describe the full story. The stress distribution gives details that we cannot get otherwise about the stress that the VWF undergoes. The point of injection is important, as well as the stress history. And with that, let me thank the National Science Foundation, the Supercomputing Center at Oklahoma, and the AICHE for their computational and support. I'll go back to the conclusions and I will stop my presentation here. Thank you so much.